Good morning students. Today we are going to see ADC, analog to digital converter. In this we are going to see direct type ADC. Now we are going to see parallel comparator flash ADC converter. We can see this is simultaneous type. Simultaneous type ADC, because all the converters, all the comparators works simultaneously. This is simple ADC converter, faster because this comparator works simultaneously. That's why we can say this is faster. Most expensive. Now we are going to see the block diagram. We are using 8 comparators and 8 line to 3 line priority encoder. This is MSB bit, this is MSB bit, most significant bit and least significant bit. This is comparator. It compares analog voltage with reference voltage. We are using equal value for all the resistance here. Same value. 0 volt, 1 by 8 VR, 1 by 4 VR, 3 by 8 VR, 1 by 2 VR, 5 by 8 VR, 3 by 4 VR, 7 by 8 VR. Or we can see 6 by 8, 5 by 8, this is 4 by 8, 3 by 8, this is 2 by 8, or 2 by 8 VR. This is nothing but operational amplifier. Operational amplifier used here does act as comparator. It compares a reference voltage with analog voltage. This is our reference voltage. Reference voltage is applied at negative terminal. Negative terminal, in this we can apply reference voltage. In positive terminal, apply analog voltage. So this is our analog input. A to D converters converts analog input directly into the digital output. Here we are using 8 line to 3 line priority encoder. So if it is 3 bit means 2 power n minus 1 comparator we need. That is 2 power 3 minus 1. That is 8 minus 1. 7 comparator we need. 7 comparators we need. Here we are using 8 comparators. So here we have to apply 0 voltage because we are using 8 line to 3 line priority encoder. So we are using one more comparator. 8 inputs we need. That's why we use this comparator, but we have to apply 0 volt for this. Here this terminal voltage, the negative terminal of this input voltage is 1 by 8 VR. How we got this means across this we have to take. Across this we have to take. Now we have to apply 0 volt for this because we need only 7 comparators. We are using 8 line to 3 line priority encoder. That's why we are applying 0 volt here. How you got this 1 by 8 VR? Any idea? Using potential divider rule. Across this you have to take the voltage. Across this R you have to take. So R into VR. This voltage R into VR divided by addition of this resistors. All resistor values are same here. So 1, 2, 3, 4, 5, 6, 7, 8. 8 R. So what we get now? VR by 8. So 1 by 8 VR. So that is 1 by 8 VR at this node voltage. We got 1 by 8 VR here. Here we got 2 by 8 or 1 by 8 4 VR. That is, now we have to take across these two R. Across these two R. So 2R into this voltage VR divided by 8R. So this is 4. VR by 4. So 1 by VR. So that voltage is here. Now the next, this node voltage, this point. Now we have to take across these 3 R. We have to take across these 3 resistor value. So now you will get 3R by 8R. That is 3R into VR divided by 8R. 3R into VR divided by 8R. So 3 by 8 VR here. Like that you have to calculate all the node voltage here. At the negative terminal, this is your reference voltage and this is your analog voltage. Now this comparator compares this analog voltage with this reference voltage. See the calculation. Now that comparator compares analog voltage with that reference voltage, that is VA analog voltage greater than VD. Here that D represents that reference voltage. Your output should be 1. If VA is less than VD, means your output is 0. VA equal to VD maintains its previous value. So this is your comparator output. Our output should be ones and zeros because the output is digital. So VA is greater than VD means output is 1. VA is less than, that comparator compares analog value with your reference value. This is your reference value. Compare these two voltages. If it is analog voltage is less than means output is 0. Analog voltage is greater than when compared to reference voltage means output is 1. VA equal to VD means it maintains previous value. So this is your comparator. Positive terminal and negative terminal. We are applying positive terminal to VA, positive terminal. We are applying analog voltage, and negative terminal we are applying reference voltage. So this is your output X. Line to 3-line D priority encoder. So truth table for this. Input voltage VA 0 to VR, then VR divided by 8 to VR by 4, then VR by 4 to 3 by 8 VR, then 3 by 8 VR to VR by 2, then VR by 2 to 5 by 8 VR, then 5 by 8 VR to 3 by 4 VR, then 3 by 4 VR to 7 by 8 VR, 7 by 8 VR to VR. X7, X8, X6, 7, 6, 5, 4, 3, 2, 1, 0. So 8 output, then your digital output is 8 input and 8 3 output. First bit X0 is 1 means your output should be 0 0 0. Then the next one, output is 1, input is 1, here the output is 1, the remaining terms 0. Here now X2 bit is 1 now. So your output should be 2, priority value is 2. Then now your input is 3. The output is 3. Next your bit is X4 is 1. So your output is priority bit is 0 0. Now your input is 1 here. You cut பண்றேன் பாருங்க, ஒரு mistake பண்ணிருக்கேன். 6, 4, 5, 0, 1, 2, 3. Cut பண்ணிக்கலாம். Now run. This is your input voltage, analog voltage, VA. This is that comparator analog voltage. Now this is your node voltage, analog voltage. We are applying analog input. That is 0 value is 1 means your output is 0. Now you have to apply x1 equal to 1. Your output is 1. Then x2 equal to 1. Your output is 2. Then x3 equal to 1. Output is 3. Then 4. Output is 4. Then your input is 5. Equivalent value here is 5. Then you are applying 6. Then output is 6. Then your input is 7. We got 7 here. Now we are going to see the advantage, disadvantage and application of flash type ADC. Advantages. Very high conversion time. Advantages: very high conversion speed, simple operation because it works, all the comparators works simultaneously. So conversion time is speed. So simple operation, no clock circuit is required for this flash type ADC, suitable for high frequency applications. Disadvantages: requires large number of comparators. We need this much comparators we need. Suppose if it is 3 bit means 2 power 3 minus 1. That is 7 comparators we need. Suppose if it is 4 bit means 2 power 4 minus 1. So this much comparators we need. So requires large number of comparators. Power consumption is high. Circuit complexity, increases with number of bits. Number of bits increases means circuit complexity will also increases. Cost is high. For higher resolution. So this is the disadvantages of flash type ADC. Requires large number of comparators, power consumption is high, circuit complexity increases with the number of bits increases. Cost is high for higher resolution. Now we are going to see applications of flash type ADC. Applications of flash type ADC. In digital oscilloscopes, applications in digital oscilloscopes, then radar systems, video signal processing, then high-speed data acquisition system. These are all the applications of flash type ADC. Now we are going to see the problem in 555 timer, astable multivibrator. Write the question, students. In the astable multivibrator, RA value was RA equal to 6.6 kilo ohm, RB equal to 3.3 kilo ohm, and C equal to 0.1 microfarad. Calculate T high, T low, calculate T high, T low, free running frequency and duty cycle D. First one, now we are going to calculate T high value. T high equal to 0.693 into RA value and RB value, substitute here, and C value also it is given in the problem. Just substitute with unit, you will get T high. So now our value is RA value is 6.6 kilo ohm into 10 power 3 plus RB value is 3.3 kilo ohm into 0.1 microfarad. 0.1 into 10 power, micro means minus 6. Answer is T high equal to 0.686 millisecond. Then you have to calculate T low value. T low equal to RB value and C value that is given in the problem. Just to substitute here, you will get T low value. So your T low value is to RB value is 3.3 kilo ohm into 0.1 microfarad. Answer is T low value is this is T low, 0.229 millisecond. Then third one, free running frequency. Now you have to calculate free running frequency. Free running frequency F. T equal to, we know T equal to T high plus T low. We will get total time. So T equal to, you know T high value and T low value, just substitute here, you will get capital T. From this you can find free running frequency. We know F equal to 1 by T. So substitute this T value, 1 by this T value, you will get free running frequency value. Very simple problem. So T high value is 0.686 millisecond plus 0.229 millisecond. Unit is very important. 0.915 millisecond. This is your capital T. From this you can find F equal to 1 by T. So 1 divided by 0.915 millisecond. Answer is F equal to 1.093 kilohertz. Or they are given A stable multivibrator, or directly you can use this formula also for free running frequency. You can use F equal to F equal to 1.44 divided by RA plus 2 RB into C. Using this also you can find this one, because you know A stable multivibrator frequency value 1.44 divided by RA plus 2 RB into C. Now you know the value RA, RB and C, just substitute here. 1.44 divided by RA value is 3.3 into 10 power 3 plus 2 into RB value is 3.3. 3.3 into 10 power 3 into C value is 0.1 into 10 power minus 6. RA value is 6.6. So just to substitute here RA value, now you will get 1.093 kilohertz. This is your free running frequency. Your answer is F equal to 1.093 kilohertz. The last one, you have to calculate duty cycle D. Write the formula for D. Duty cycle D equal to T low divided by capital T. T low divided by T value. So this is RA plus 2 into RB. Now you will get 0.25, that is D. We can say this is 25% duty cycle. 25%.